So yeah, first of all, let me thank you and thank you to be here first and to allow me to give this talk. It's a good opportunity for me to introduce my works and my future works also that I would like to do here, among other ones. I'm Dirian Yves. I did my PhD with Michele Maggiore in Geneva in 5 years. Then I went 2 years in Zurich with JU Liu. And then I received this FNS postdoc mobility fellow from the Swiss National Foundation to do with a project with Deser for 2 years, basically. So I'll tell you about two different subjects. So they have nothing to do together. The motivations are maybe linked in some way. The overall motivations is to understand gravity in the infrared regime. So what's going on in the very large scales of gravity. And in particular, when we are looking at large scales, we look at cosmology and cosmological observables. So first, I will present you first part of this non-local infrared modification of gravity. Then I will do a second part with the presentation of works that I've done in Cosmological, Numerical, Relativity 2, which I included. So basically, the Cosmology group can enjoy the first part and the Grit group can enjoy the second one, mostly, I would say. So let's start with the general introduction. So we are interested in understanding the late time accelerated expansion that was described. Since then, so this led to the introduction of the so-called cosmological constant in an Einstein equation, which is a building block of the cosmological model, the standard cosmological model, lambda CDM. And actually, it's the simplest option that is compatible with the symmetries of the theory. And it's also actually the one that works the best. So it's nice. And this has been confirmed through the years with more and more precise cosmological observations, like the ones from the CMB, but also like galaxy clustering, like the BAO, reticulated distortions, and so on. And when you use all these probes all together, you can combine them in a complementarity way, like on this graph. And if they all intersect, if all the images intersect in the same spot, then it means that your model is nice and you have a concordance. That's what we partially have, say, with lambda CDM. But still, there is a theoretical problem and also potential observational ones. First, there is the well-known cosmological constant problem, which reflects basically our understanding of the fundamental vacuum. So what the fundamental vacuum is, which is probably linked to quantum gravity, but also to the hierarchy problem, etc., in particle physics. There is also people that say that there is a coincidence problem that violates basically the cosmological principle. So that for the theory and on the level of the observations that we have done, recently we have seen some statistical inconsistencies in the lambda CDM model. First, the most prominent one is on the Hubble constant, H0, predicted between the CMB and local measurements, especially from from stars from the local group and supernovae, but also from strong lensing measurements. There is also tension. There is also other parameters on which there is inconsistencies, like on the growth of structure, sigma 8, between cluster counts, so CMB2, and weak lensing measurements, and also on the potential ISIS, they say, on the curvature of the universe, given the CMB data. So there is things that don't fit so much, and that we are interested in understanding. Some people say it's systematic for the observational part, but maybe it's also something new. And so what people do is to try to understand other theories of gravity and GR, so alternatives. This is, say, a patchwork of theories that have been an example, a non-exhaustive patchwork of theories that have been investigated. So basically, to deviate from GR, you need to escape. Basically, it's a good way of classifying it. The Lovelock theorem. So in escaping the Lovelock theorem, you become either higher dimensional, you can become higher order, you can add new fields also. So you can classify all this like this. You can also become non-local. And all the subsets of these theories are also linked. So higher order can be expressed in scalar theories. Higher dimension can also be non-local, and so on and so on. So it's just a way to map a bit the landscape. And so we are working here in this non-local class that I will show you. And so what is interesting is to understand theoretically first the models, their stability and what is inside, and then to develop the methodology to test it given future current and future observables. So what we do is first the non-local gravity model. So when we say non-local, what it is, it's in a classical sense, not in a one-to-one, of course. So a theory that is non-local is basically not local. It's a bit tautologic, but what local is that you depend on the field, on the set of fields of your theory, and on the derivatives in finite number. So this is local. And whenever you don't have this, you are non-local. So it means that you have no polynomial derivative operators like this, infinite derivatives also, and a whole bunch of expressions, horrible also operators that pop out. And this comes from several domains, say, in theoretical physics, like interferometers, quantum field theory, like vacuum dressing, which is perturbative, the conformal anomaly, which is non-perturbative. There is also things like this in extra dimensions, like BGP, where you have such a square root of box field. It's also motivated by infrared approximation of the sphere and by quantum parity and so on. So basically, it's there is a lot of ways where you can correct GR at least non-locally and in the IR, because here there is infrared correction. While in string theory, these non-local corrections are more infinite derivative to soften strong interactions in UV. So it's more UV relevant. And actually, from a infrared perspective, it's really hard to understand the theory, and this from first principles. So what people try to do is to have like an EFT-like approach to test different simple operators that you can build to see what they have inside and which phenomenology they are, and if they are relevant for explaining what we observe. The problem with these non-local operators is that you can actually build, since you can invert now a mass dimension here with the derivative, you can build this kind of operators that are dimensionless. So basically, in an effective approach, you would say, okay, this I can put power 1, power 2, power 3. So you are suppressed by a mass, and every time I put a power more, there is a suppression more of the mass. But here it's dimensionless. So power 10 or 15 is the same. It doesn't have a power counting. We don't have power counting rule. So the thing is, we go step by step, and I will present you 3 models in particular. So 2 that were presented by my PhD supervisor, and another one which is more classical, which was proposed by Deser-Woodard in 2007. So, and these basically the models that I will show you, the 2 first ones, they are inspired by the degradation idea. So it's a bit long to go into the details, but basically what is the heart of the idea is, since we have from the standard model of particle physics a vacuum energy that is really big, predicted, you can say that in the UV I have this vacuum energy, and whenever I look at the IR, then this vacuum energy degravitates, so it loses its coupling to gravity, and so basically it gets smaller effectively on a larger scale. And a way to do this is to trick the. Or you can also give a mass to the particles, which is the same with this U power exponential coupling that you have, you can basically give the mass to the particle so that the long-range interaction of massless particles becomes short-range, and so you couple to a shorter distance with your with the vacuum. And this, so it's quite interesting that in such theories, so this is the Procca-Lagrangian, you can actually write it in a non-local form. And actually, you can see here this term breaks the U1 invariance. And actually, if you give up locality, you can recover U1 invariant because this one F mu is total invariant. And the current also gets saved by something which makes it from that. So you restore basically the gauge symmetry in giving up locality. And actually, you can see if I write this term here. So this is just F mu, which is the massless photon. And this is 0 when the box, which can be considered as the energy of your theory, is high. So when the energy is high, I mean the UV, I'm behaving like the massless field. And whenever the energy becomes comparable to the mass, they can really big fields. This becomes effective, and then you have this U power damping. And so in vacuum electrodynamics, like this, people have tried to do it also in massive gravity to eventually find the covariant version of massive gravity. But then you fall into the caveats of gravity of massive gravity because you find like covariant version of these BDBZ expressions. So basically, this theory doesn't work. However, you can explore closely related theories to this, which takes this form, which has been developed in this reference. And actually, here you take this this filter, say we could call it a high pass filter because it moves past the UV. You plug it in front of the gravity. So basically, you just modify the infrared factor of your theory. But here, when you covariantize, the covariant derivative doesn't commute anymore with the box. And so you should put the transverse part. This is possible here. That's what the people do, actually. And actually, they realize that inside here, the big diminu, there is instabilities generated by generic tensors like this, which is like tensor instabilities in non-local gravity, which has been investigated in this paper. Whereas this term is stable, the term with the rich scalar, and basically we have this theory. So from this theory, we can derive another one, basically because there is no action. So you can go to Minkowski, derive an action there, and you covariantize it again. So basically, the nonlinear theories are the same, but they have the same Minkowski linear theory. And you get another theory for free, which is this one. So that's for the, I should speed up. That's for this one. So we have basically two non-local theories. But we are now, I should also say that we looked into the theoretical structure of the theories. So we looked at the spectrum, at least on Minkowski. And actually you see that there is the spectrum of GR. And here you have the relics, so that's the mass of the graviton, which is the relic of massive gravity, but which is now a massive scalar, which has the wrong kinetic sign. So that's the bad news because wrong kinetic signs are instability. But it's also a good news for here because I tell you also that there is no BDBZ distributivity. So when you send the mass to 0, then this propagator cancels, and you just remain with 0. So basically, that's what you should have at small scales. And since the theories are non-local, actually these poles are coming from the non-local operators, and they are not considered as degrees of freedom in the spectrum of the theory. So basically, you cannot measure these particles, and they cannot really get interpreted as particles. That's what the statu quo of this understanding. Yes.
One slide. So at the top here, if I understand well, when you write economia, is you're saying that the solutions to the Procca theory that the solution space is the same as the solutions to the modified thing on the right.
Classically, yes.
Okay, so given that that's the case, why would I want to non-localize it and work with the non-local version instead of I don't really see why I want to do it.
Well, it's a way of restoring gauge invariance also. That's what's interesting, because people used it in massive gravity. Because in massive gravity also you don't have gauge invariance, first Pauli gravity, but you can restore gauge invariance, and that could be a good strategy to covariantize the theory. If you have gauge invariance, you already have something to covariantize. So that's the U1 here, gauge invariance, and here it's linear differential. Okay. Right. And so basically we are interested in studying the phenomenology of this. So here it's integral differential equations, basically, but there is a way to deal with this without solving integrals, basically, because it's quite hard. The trick is to introduce auxiliary fields, so that basically, if you want to put this one over box operator here, you just introduce a field whose solution is box equals R, and then this, the solution of this formally, is given by one over box here. The Green's function, you can choose whatever you want. And then there is some homogeneous modes here. But whenever you fix your initial surface, you can here choose, say, in my time direction, I'll choose the retarded Green's function. So this fixes the Green function unity. And you are forced to impose vanishing initial condition of three guys. So basically, it's a propagating constraint that you add in your theory that this guy should be 0, and they stay 0 throughout the whole evolution. And then you introduce this field in such a way, you have the local versions of these theories that you can now specialize on a cosmological background. Then you derive the modified Friedmann equation, which relates the Hubble parameter to the energy density. And you see actually that you have an extra energy density that now is proportional to the mass square, which is this non-local operator, which generates actually for you an effective dark energy density, which grows like the cosmological constant at very late time. You can see here. And actually, so it's a dynamical dark energy because it starts from 0. And it starts from 0. Why? Because the Ricci scalar on FRW in radiation is conformal, so it's 0. So the background is 0. So there is nothing going on before matter sets in. And once you have the matter that sets in, you have this curvature, non-local curvature term that starts to count. And then you have a dark energy density by rho with an equation of state that is on the phantom side. So there is this RT model, which is, sorry, I didn't tell the nomenclature. So you have the RT, which is this one with the transverter, and the RR, which is this one with the RR thing. And actually, the RT1, it's phantom, so less than -1 for the equation of state. Lambda, the cosmological constant is at -1 here. So we have the RT, which is phantom, and the RR, which is even more phantom. And this will change the phenomenology on the background level, because you can actually check that if you have a phantom dark energy at fixed redshift for the small same cosmological parameters, you have the dark energy density here in the expansion rate, which is smaller. It gets smaller once your dark energy dominates. This is the redshift. This is the relative difference in age. So you can see that the more phantom you are, the more you reduce the Hubble expansion, and therefore you also like largen your distances. So etc. So there is a whole set. Sorry. Yes.
In such sense, with no contribution of the advanced Green function, you only have a relativity Green function, but is there a contribution of the advanced Green function?
That's a choice, and actually, you classically, Formally, for it to make sense to have causality, you should take the Green's function, the retarded one, at classical level.
Okay, you that's true.
That's what comes out if you do the in formalism. It comes naturally out that you want. Okay. So basically, your phenomenology is changed for the background, for the perturbations too. So I put one slide here. So the growth of structure, basically, the more phantom you are, always the red curve here is RT. The more growth you have. So here we have RT, which has 2% more growth, and RR, which has like 5% more F sigma 8. And this is basically due to the fact that since you have less Hubble friction, you are collapsing more, basically, and so you have more growth also. And actually, people did n-body simulations, and they found out that the dark energy perturbations are not affecting too much the growth. It's only the background effect that is predominant in this theory. And that's what we call a smooth dark energy component, which is phantom. So it's quite a general, type of phenomenology that we know. And you can also look at the GBs, at the gravitational waves. Actually, here you see that nothing is changed, but you just have a term that modifies, that modifies the friction term, that modifies the amplitude. And since the amplitude is linked to the luminosity distance, you will see that this has implications also later. So now, since the phenomenology went quite well, we implemented the model in a class, which is a cosmological code that solves whatever you want for the cosmology, at least, and allows you to do parameter inference, so to compute the observables and to directly compare them with data. So we did this, and from this, you can sketch this triangle. So basically, that's the cosmological parameters that we are learning, which is baryon, cold dark matter density, the Hubble constant, and then things related to primordial purity and the realization redshift. And you see actually from the inference here that everything is quite superimposed, but for H0. And actually, the more phantom you are, the higher H0 you prefer. So that's basically linked to the fact that you lower the dark energy density. So to compensate this lowering, you need to higher the normalization, basically, which is H0. And also the growth is a bit shifted. And actually, you can see that it fits quite well. So the linear circuit is quite good when you have just Planck. But if you add the supernovae, the more phantom you are, basically, the more you are excluded by the data. So that's bad for you. And that's because basically the CMB constrains really well this combination. So that's the cold dark matter density, and that's the Hubble. And actually, the line of the CMB is here. So since it's really well constrained, if you lower the dark energy density, you need to higher H. But if you higher H, you need to lower the cold dark matter density. And actually, for the supernovae, it's the opposite. So you see for the phantom, the more phantom you are, this goes to the left here. And actually, the red one goes to the right. The more phantom you are. This you can check. You can find the mechanism to basically solve this tension that opens here. And actually, a mechanism to solve it is to vary other parameters that are fixed in lambda CDM, like curvature or massive neutrino, the mass. Actually, I did this with the massive neutrinos, and it works quite well, because at the end, you re-establish the concordance. So you have now an insignificant base factor between lambda CDM and the nonlocal model. And the nonlocal model actually predicts a non-vanishing neutrino mass at 2 sigma, which is quite interesting. And it best fits at 0.2, something like this, 0.2 electron volt. So basically, if you change your equation of state, you lower, or you change your background phenomenology for FRW, and you can have other predictions for curvature, neutrino mass, etc., which shows that these parameters are basically depending on the dark energy model that you consider. So basically, when people say we measure the neutrino mass, they say in lambda CDM. I did also other studies. So in non-local gravity, in particular in this Deser-Woodard model. Here it's a bit more messy because you have these three functions that people chose so as at the background level you reproduce FRW, lambda CDM, sorry. So you have exactly lambda CDM on the background. And this is done in such a way so you can find, you plug it H lambda CDM in, you compute this machine, you have F, you have X, then you have F of X, X is the argument of it. And then you reconstruct it. So for the background, you have the same as lambda CDM, but for the perturbation, it's different. So that the growth is F sigma 8 again. And actually, here there is less growth in this model. And you can see that the tension between mid-lensing, that's the kids, and Planck, in this sigma 8 omega m plane, gets weakened in this model. So it's also quite fitting well the observation as well as lambda CDM. So we can make something working at least. However, there has been shown that there is a lack of screening in this model because essentially the authors, Deser-Woodard, did a mistake, a computational mistake in proposing their models and in proposing the screening. The screening they proposed didn't work, so basically there is no screening implemented. So we don't really know, and it doesn't have been studied, so we don't really know what's going on. Then what we also did is to study the small scales. So when everything goes well on large scales and you have a phenomenological variable dark energy theory, say, you should also see if it reproduces GR on the small scales to agree with what you observe basically on these scales. And so there is different ways to do that. The first approach that has been taken is to consider a static and symmetric Schwarzschild-like solution, basically, where you can show that the corrections to GR are of order m squared r squared. So basically, when m goes to 0, you reproduce GR, and if the mass is really small, then you have GR also. However, there is no discontinuity, which we know from the propagator on the Cup. And then there is also a question, since there is no discontinuity, there is no Weinstein mechanism to protect it, like a non-perturbative mechanism of screening. So what would ask, what is the screening mechanism in these theories? Actually, we don't really know. And it has been shown also that that's a bit more technical. If you look at the Poisson equation on FRW, so that is, if you look at small scale solution where you don't have time derivatives, sorry. Actually, it has been claimed that this RR model and even the Deser-Woodard are ruled out by lunar laser ranging. I don't want to enter too much in the detail, but I think these results are a bit premature, and we should think a bit more about it, basically. However, the RT model, so these are a bit confusing, say, but the RT model has the good behavior in this regime. So basically, it satisfies all submitted tests that we did. And it does quite a lot already. And for this reason, it has been considered by the LSST and LISA collaboration. And that's what I'm aiming to do now, is to test more, because basically, all what I've told you now is that the model has been tested on small scale, okay? But only in regimes where basically the non-local correction was really small. Like this, basically, it's the non-local term K over H. It's this for the background. So this is big, so this is small. And non-dynamical also. So now what I would like to do is to check, and that's what I'm doing here, where you study nonlinear and strong regime gravity, is to test this model in regimes where the curvature is at the same level of the energy, say. And this would allow for new tests for the screening in the theory, and to see if it's compatible with what you observe. So there is combinatorial tests first, if there is equilibrium solution for stars. We can also look at the quasi-normal modes. We can also look at the cosmological corrections, and eventually also at super instability, because there is we have like a scalar poles beside of the one of the gravitons, so probably there is a super and also some theoretical tests that you can do is that is the model well posed, and also how well posedness say is defined for non-local theories, and also nonlinear analysis and so on to see the spectrum of the theory in the nonlinear regime. These days we are also doing forecasts for stage 4 galaxy surveys. So that's basically technical. I'm contributing for this. I'm generating the observables to compute the feature matrix. And then we want basically to see if future galaxy survey observation like Euclid or SKA will be able to discriminate between the lambda CDM and whatever non-local model that we want to test. So basically, that's what I'm also doing these days. Then there is also this new model of Deser-Woodard that now is supposed to have screening that they proposed. This also needs to be studied. And then I have also done a part with gravitational wave experiments at cosmological scales. So as I was telling you before, you can use the gravitational amplitude that you measure in the detector to access the luminosity distance in GR. And so you can basically reconstruct the Hubble diagram with gravitational waves. And actually, this Hubble diagram, you can compare it to the ones of supernovae, for instance, and you can see if it's the same. And actually, in modified gravity, where you have this kind of modification, you go through the same computation, and you actually see that there is another version of the luminosity distance for this modification of gravity. So it's linked to the electromagnetic one that we had before, times the term which shifts like this with this function, this delta function, which intervenes. And we actually tested the parametrization of this effect like this, the combination parametrization. And then you can forecast how this will be constrained with respect to the equational state of dark energy. So this modification either modifies the background, so that's the dark energy that you measure. This modifies the perturbation. And actually, this modification of the perturbation, we found that it could be measured 6 times better than the dark energy equational state. So this is really like a better smoking gun for non-standard gravity, I would say, if it exists for. It's a new kind of cosmic complementarity also. And what I should say is, what we found also in this study is that basically the cosmic explorer or ancient telescope will observe millions of sources, but we don't have enough GRB detectors. So basically, the number of sources that you have at the end is reduced by a number of 10 to the power 2, 10 to the power 4, depending on how you do the assumptions. So basically, we need more GRB detectors, optical detectors, to see more gravitational waves and standard sirens. What I would like to do here is to look at different multiples of this luminosity distance. So this has been done already, like you can consider the dipole and higher multiples. And from here, it has been shown that you can actually directly measure the expansion rate at a fixed redshift, not an integral, but really the function, the actual function. And we could also actually apply this to the luminosity distance in gravitational waves, and to see basically how also linear perturbation influence these observables, to have more information and to basically improve these, we can still improve these constraints. Now, for the time that is left, I will talk about general numerical relativity applied to cosmology. So what we have done here is to basically go behind what we do usually in cosmological simulations. That is Newtonian n-body for the clustering of matter, and linear Einstein Boltzmann for CMB, and for linear structure formation also, and so on. And what we would like to do is to put GR here, to solve everything together and to see what we have new, and especially so relativistic and nonlinear effects for structure formation. This has been investigated already in some ways, like on Newtonian simulation, it has been like relativistic fluids have been added. Some averaging have been done also to see if we have some like background back reaction, things like this. People are also interested in relativistic corrections, so that's based on this perturbative method that is implemented in the G-evolution code or in Gramsci. But people have also done, so that's perturbative, but people have also done the full non-perturbative treatment of early universe, like stellar inflation models, or pressureless perfect fluid, so cold dark matter for the late universe. So it's quite an active, it has begun to be an active field this past year. Actually, they have also been the general relativistic n-body simulations already. And also they are comparing the code, so it's developing. What we try to do is to develop also basically n-body code, which is general relativistic, to have access to non-perturbative structure formation observables, basically. So how we do this? So we need to solve Einstein equation. So this, you write the system in 3+1. This most of people know. You put a formulation, you evolve basically forward in time, given some initial data. And the initial data now are cosmological. So we have a cube with the primordial fluctuation distributed, and we want to evolve this with Einstein equation. So you know that, probably know that these equations are hyperbolic if you do the standard IBM decomposition. So you need to make some watchmaking, say, to make it work on a computer, like in the BSSMC. You need to massage the equation to make it strongly hyperbolic. There is several ways to do this. And actually, then you need to test the code, and there is several ways to test it. A way that we chose in our project was to take this apple with apples comparison tests, which test background vacuum solution on Relativisti, linear wave, but also non-linear solutions like wave or the body wave. And we have basically these test benches, but these are usually used in strong gravity, where you have asymptotic. Here we have matter everywhere, so you are never in vacuum, right? We have no symmetry, so we have something that is 3D. And you have a new effect, that is you have a growth, something that grows all the time, a mode that is basically always there, and this is all numerically hard to handle, basically in the computer. This has been shown with some fluid approach, because I told you that in GR we have the metric evolution, we have the matter evolution, that you can just evolve separately, and then you are obliged to respect the constraint. You can also evolve the metric, take the constraint, check the matter evolution, there is plenty of ways to do this. But basically, if you take the solar approach, BSSN synchronous gauge, there is some errors that are propagating, at least with the fluid in the pressureless fluid in the box. So people have tried, and we did also, to design some schemes that are more adequate to cosmological initial conditions, to cosmological settings. And this decreases the constant violation side, but it's still not acceptable. And also, so for the fluid codes, when you take hydro, you have a good advantage because it's easy to implement and there is ready codes. But still, you have an inconvenience because you are limited in your physical, in the reach of your physical descriptions. And actually, you cannot describe shell crossing. That is when the particles meet together. You cannot describe this. It becomes basically singular. This shell crossing in this formalin. There is no vorticity also. And basically, you have a non-realistic structure collapse. So it's better to do the end body. This has the advantage of taking all the nonlinear processes into account. However, it's also really complex. You have a particle mesh method that could spoil your constant violation, etc. You have more sorts of error generation, basically. So basically, this has never been done, and it could. We don't know what's the answers. Some people say there is a trivial answer. Some others say less trivial, we don't know, so I think it's fair to do it. So we developed a code to do it. Here are some technical details, but I will not go too much in the details, maybe. So what we did is basically we selected the most promising numerical relativity scheme that we tested against the Apple test, as I showed you before. So we are basically for the particles solving the geodesic equation. So you make move the particle, you project them with the clouding cell or triangular shape on the grid. So you make a field of it. This field we take derivatives with 5-point stencil. We evolve in time with Ruby 4. And for the initial condition, we take the power spectrum of class. So we generate a displacement field using Zeldovich approximation. We generate the primordial power spectrum, say. We make it evolve from redshift 1000 to 0. These are all the equations that we put in the computer. These are all the parameters that we need to tune to have something that works. This is the way we parallelize the grid with this library, which is a Relativity, which has been developed by a collaborator of mine. So basically, this is all MPI parallelized and does all the data handling really fast. So the grid is basically divided into French files like this. Here you have nodes on each French file, and you have communication among the nodes to your hardware, basically. And so that field organizes all this. Right now, it's a fixed grid. We can have periodic, so torus-like or fixed boundary conditions. And so now we don't have node hours, but we did a lot of intensive computation at Piesdent in Switzerland. And basically, we were able to evolve. So let's say structure formulation from redshift 1000 or 100 to 0. So we did it. That's the result that we have. So we see that we are able to resolve the walls, filaments, dots, and so on. This is 50 megaparsec. So it's like k equal 1. So it's quite nonlinear already. And these are the corresponding. So what we are constantly checking is the constant violation first. So this is the Hamiltonian constant violation. This is the momentum constant violation. It's the L1 norm, so it's summed, it's integrated over the grid. This is 64 points, 128, and 276. So the resolution is divided by 2 all the time. If you have a conversion code, everything should be parallel. Here it's not parallel starting from here. so it doesn't converge, and that's basically because we have some nonlinear behavior and nonlinear effects that we need to handle, and also with all these numeric recipes that we have, we are not able to have convergence, but still, it's not so bad actually. And we also tested other, how you can say, quantities like that are more physical. This is to see if your solution is physical. But like we tested the linear power spectrum and showed that it evolved linearly how it should, up to 10 to the minus 2, something like this. And we did also energy conservation. The energy is conserved to 10 to the minus 2, 10 to the minus 3, too. So it's not, we are not far, say, but still the code is not so robust. And this needs more sophisticated methods like relative mesh, moving mesh, or evolved things like this, or even changing the way we take derivatives, finite elements, etc., which is really heavy. And we also need data processing methods to extract the observables. That's already done in the library, because there is other codes that use the same library. But yeah, there is a lot of things to do, and I think I will stop. Thank you.
If you enjoyed the video, like and subscribe.